Okay, a very good morning to all of you. I hope everybody is fine. We'll be continuing with our lecture on the network layer. So, in a previous class, we discussed about the IPv6, IPv4 addressing, and to continue with it, today we'll start with the IPv4, the addressing format, as well as we'll take about the structure of IP datagram. Let's go to the PPT. Hey, Ramanan, what are you seeing this time? Okay, all right. So in our previous class, we saw that when the data is passed from the higher layer to the lower layer, the data, uh, just a minute, I'm getting calls from NIT. Just a minute. So we're discussing about when the data is passed from the higher layer, that is what we have as the transport layer. It is given to the network layer, and the network layer has three main functions. One was the addressing, the second one was routing, forwarding, and third one was checking for errors with the help of ICMP. Now, sorry. Now, when the packet uh, is passed on to the network layer, datagram is passed on to the network layer, there are some functions that the network layer has to do. And those things what the network layer does, the information and other related things are kept in the header of the network layer datagram, what we have as network layer header, and there is a format for that network layer header, and that is what we are going to study as IP datagram format, in which we will see that uh, what we have within that header. So to begin with, the lower part that you see in the picture, that is this thing, this is the data field. Okay, it says variable length, typically a TCP or UDP data segment. So this field actually takes the data from the higher layer down to this lower layer. If you have, let's say, this Facebook Messenger, it gives on some data to application layer. Application layer passes on to the lower layers, and then it reaches to the network layer. This is what the network layer received from transport layer. It has the transport layers, header, etc., and so on. But all of it together forms the network, forms the datagram which is passed from the transport layer. So network layer here would add some data here which would be header. So this part is the header part. Now within this header part, this is the header part. The remaining this part is data which was received, and this is what we have here. Data which is of variable length. Now within this data, what we call as payload, typically the size of it is kept such that whatever we get from the transport layer should be adjusted within this. is the example that I gave, the truck example. That truck has a carrying capacity of 1500 bricks. So normally the transport layer would give 1500 bricks to be transmitted per packet, so that the truck doesn't have to come twice, in the sense that if it's 2000 bricks, truck first takes 1500, then it takes 500 more. Typically it's done that way. However, there can be, instances wherein we get a datagram which is bigger in size. So in this case, for example, if we get something like this, which is more than 15, this is to be broken. In one end we will have 1500, and then we'll have the remaining one. Now again, the question here, why do we choose this as 1500? There is a reason for us why we choose this as 1500 here. So why do we choose 1500 bytes here? Anybody? My question is, we choose here the data length as 1500 bytes. Any reason why we choose this as 1500 bytes here? Plus one for this answer. No? The reason being that we saw that there is MTU in data link layer as well, what we know as maximum transfer unit, and that is of 1500 bytes. That's why we would want that whatever we get there adjusts within the same one. Otherwise, there has to be, we have to break the packet into a number of pieces. That is known here as fragmentation. So whatever we got the data from the transport layer, we put that here. This forms the data that we have. That is the first part. That is the data. To begin with, the first one here is version, VER. It's IP protocol version. What protocol version are you using? In the sense that there are two different protocols which are widely used presently. One is IPv4, another is IPv6. It's a 4-bit field, okay, which informs us whether this datagram belongs to IPv4 or whether it belongs to IPv6. The next field after this we have is header length. This is again of 4 bits. So a total length here is of 32 bits. This is 4. This is again 4, making them 8. The length again is of 16. All right. 24. Then we have 8-bit type of service. Now, what is this? What is this type of, what is this, the second part, that is the header length? This actually a 4-bit field needed to determine where in the IP datagram the data actually begins. So it will give us header length. And you can see from here, from the picture here, this part is header and this part is payload. All this information that is given within this header constitutes the header as well as trailer altogether. And the remaining one would be the payload or the data that is actually to be transmitted, which we get from the transport layer. The third part that we have is type of service or TOS. Be clear. This is the third part. The type of service is actually included in the header to allow different type of IP datagrams. For example, a datagram might require low delay. A datagram might require better throughput or high throughput. A datagram might require better reliability. That all is to be mentioned in the type of service. It's important. Why? Because we need to distinguish between real-time traffic from real-time traffic. Real-time traffic like VoIP, telephony, or you're watching, a cricket match and things like that over there. Compared to some service like FTP, which is a non-real service. So that is to be mentioned within this type of service. And then comes the length. That is what we know as the datagram length. The length, datagram length is the total length of IP datagram. So I'm discussing about this datagram length. This is 16-bit. Now this gives the total length of IP datagram. Total length in the sense that it will give us the total of header plus data or payload. This gives it in bytes. And how much length do we have? What do we expect within this header? Theoretically, we can expect it to be 65,535 bytes. But in reality, we do not get that much length. In reality, we would get the length of how much? Anybody? I'll repeat the question. In the datagram length here, it mentions what is the total length this of the datagram, which has the data as well as the header. Theoretically, it's 65,535 bytes, but in reality, we do not keep it that much. How much should we keep it? Mehreen says 63,535. What is the reason, Mehreen, for it? Why do you decrease this 2,000 bytes? Any reason? Anybody else? I gave an answer in today's class itself. No? In reality, it's 1500 bytes. And what is the reason? The reason is again the same. TU. If you give, for example, 2000 bytes, then you would have to fragment the data layer gets the data which is more than its carrying capacity. The maximum transfer unit is 1500 bytes. If we get something bigger than this, it would obviously have to fragment it. It would have to break it. That is what we have here as length. Okay. The next part that we have after datagram length is the 16-bit identifier, the flags, as well as fragmentation offset. That is this part, which I would denote in yellow. This part. So this is required when we go for IP fragmentation. And what is basically IP fragmentation? Is the same thing what I just now discussed. If now the transport layer gives the data which is of more size than the maximum carrying capacity of the network layer, then network layer has to break it into 1500 bytes each. It has to break the data into less than 1500 bytes so that it can meet the carrying capacity of its own layer as well as the lower layers, that is the data link layer. So if we have to break it, then we would use IP fragmentation. We'll be taking up more of it later. Then we have the next one, that is the time to live, or TTL, that is given here. TTL ensures that datagram does not circulate within the network forever. So you give a certain value to it. Let's say you give TTL 10. It is decremented at each router, means after every hop we get a -1 within this TTL. So TTL changes every time it moves from one hop to another hop. Keep that in mind. Once it changes at every hop, after the 10th hop, it gets 0. Once the value is 0, it is dropped. So this is how you would ensure that the datagram does not circulate within the network forever. Why? TTL field reaches 0, datagram should be dropped. The router that gets the packet with TTL as 0 would ensure that packet is not forwarded after that. The next one is the upper layer or upper layer protocol, simply known as upper layer protocol. What is upper layer protocol? It is used when IP datagram reaches its final destination. Value of this field indicates the specific transport layer protocol to which the datagram is passed to, which means here you are giving an indication of what higher layer protocol it is expected. It's like a glue. On one end we keep the layers different, we separate the layers, but on other end there has to be a glue between the different layers which binds the network layer and the transport layer here, in the sense that if you have an upper value here 6, it indicates that you are going to pass it to TCP. TCP is a protocol of transport layer. If the value here is 17, it indicates that you're going to pass it to UDP. This packet belongs to UDP, which we are going to study in our forthcoming classes about TCP and UDP. After that, we have what we know as header checksum. What is header checksum? That is this one. Header checksum is basically helping a router in detecting of errors if we have bit errors in the received datagram. Typically, we studied about internet checksum. So it is about internet checksum. If a router computes the checksum here and finds out that there is an error, generally router would discard the datagram if the error has been detected. This checksum helps in detection of bit errors. And also, another thing, important point to note here is that checksum must be recomputed and stored again and again at each router. Once it passes to another router, checksum needs to be recomputed and restored within this. Can anybody tell me what is the reason that checksum needs to be recomputed and stored again at each router? Plus one. I repeat the question. Checksum must be recomputed. This is what we're talking about, internet checksum. It must be recomputed and stored again at each router. Why so? Why do we need to recompute it again and again? Okay, Mehreen says for error detection. Yes, for error detection, but why do we need to recompute it again and again? The reason. Akif says error introduced in one link is not passed to next. Error introduced in one link is not passed to next. Yes, error checking, for error checking, we do have this checksum. But my question is, what is the need of recomputing and storing the header checksum? One is, yes, you did the header checking, that is fine. But why is checksum to be recomputed at each router? What change is there? That's a hint. What change is there within the header that makes it recompute it again and again at each router? That should give you a clue. IP address, Mary? No, not at all. IP address of the source and destination remains as it is. It is not like the MAC address that is to be changed after you have to pass on the datagram beyond the router. MAC address is to be changed based on the networks you move out. But IP address, source and destination is kept as it is once it is to be transmitted from one place to another. If it's changed, it cannot reach the proper destination. Anything else? Should not be that difficult. Ramanand, hop limit might change in every single hop. That is correct. Nawazish, yours is also correct. Hop limit or TTL changes. So both, okay, Nawazish and Ramanand, I'll give you one to each of you. Yes, TTL. Ramanand, you get one, and Nawazish, you get one. I just now mentioned that TTL changes. It decreases. So yes, that's the correct answer, because change in the TTL makes the header checksum to change. That's why we would need to recompute these, checksums at every hop. Correct answer. Plus one to each of you. And the next part that we have here is, well, that's a good thing. I see many of you are listening to the lecture here. The next part that we have is a 32-bit source IP address as well as a 32-bit destination IP address. This is basically the IPv4 address that we discussed in the previous class. So we need to give the destination address so that the message is delivered to the host. If we have to deliver this message to a specific system within our network, we will give the destination IP address like 192.168.1.1. Okay. And if we need to broadcast this address, this packet to all the systems within the network, then we would have to use an IP broadcast address, which is given by 255.255.255.255. This is the IP broadcast address. If you remember, we had MAC broadcast address as well. And the MAC broadcast address was FF, 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 FF. That was for the data link layer address. So this is the 32-bit source and IP address. And there is another field, the last one that we come across here is given options if any. This allows our field to be extended. We can extend our IP header field in case we want the in case, for example, as an example, you want to add some security feature to your datagram. Now, how do you implement that security? Certain things that you might have to carry on with the header can be placed within it. Another example here, timestamp, record route taken, specify list of routers to visit, and so on. All these details can be put within the options field of the header. How much overhead do we have here? We'll take the TCP's header field separately. Okay, we'll see it when we take the next layer. The IP header that we have here, I'll mention here, is 20 bytes. So we expect this part to be of 20 bytes, and each packet would add this 20 bytes to the data that is to be transmitted. Is this clear? Now comes the fragmentation and reassembly. Like I just now mentioned that every network would have its own MTU, that is the maximum transfer size, and that is what the maximum size it can have. In order to maintain this MTU, if we get a large IP datagram, that large IP datagram need to be broken down, which we call as fragment. Okay, so the sender here, if this is a large datagram, it will break it into a number of different datagrams. Okay, and then number it them. This was supposed to be 1, this is 2, and so on, and add some other details to it as well and pass them across. First this one would go, second this one would go. Once it reaches to the receiver first would receive this one, then it would receive this too. So this is, let's say, 1, this is the 2. So on one end, what the sender did fragmentation, and on the other end, once the receiver received it, it did reassembly. So we have fragmentation and reassembly, breaking down on one end and joining back on the other end. This is what we saw in the this is what we saw in this part. I think it's Abhinandu's. All right, coming back here. This part, sorry, this part would help us in the fragmentation and reassembly, which is given in this section. You can see here incoming is one large datagram and outgoing is 3 small datagrams. Here. And then we have the reassembly. And for this, we would require these fields, which is of length, ID, fragmentation flag, and offset. For example, it's given here you have 4000 byte datagram. Your maximum transfer unit is 1500 bytes. So you can send the field as the data would be 1480 bytes. Why? 20 bytes you would require for the header of the network field. So you will keep those 20 bytes saved for it. And the rest you can break down here within these three. And then you would set the fields of fragmentation on, informing that yes, you would have done the fragmentation, and accordingly you will have to set offset as well. So this uh, is about the format of IPv4 datagram. In IPv4, we saw there is a 32-bit source and 32-bit addressing. We did this addressing in yesterday's class as well. But we did DHCP as well. But the problem here arises, actually it already arose, is that in IPv4 we had the possibility of having 2 to the power of 32 possible address spaces. And when it was started, that time it wasn't imagined that we would have so many devices that would be connecting to internet. So many in the sense that nowadays even your watch comes with an IP address. There are wearable devices. There are so many devices that would need or that would require an IP address. That's why the IPv4 addresses got depleted. There was a need for a newer addressing, and that addressing was known as IPv6 addressing. There was IPv5 as well. Initially it was given, but it didn't work, so it was dropped. Then came IPv6 addressing. This is given by IETF, Internet Engineering Task Force, also known as Next Generation IP or IPNG. The main difference between the IPv4 and IPv6 is basically the header, the size of IP. IPv4 is 32-bit, whereas IPv6 was given as 128-bit. Obviously, IPv4's header was 20 bytes, which we just now discussed. Here in IPv6, we have header of 40 bytes. A number of differences like fragmentation. Fragmentation is not done in IPv6. We do not have a checksum field. We do not have options field. We have an extension header in IPv6. I have made the list of differences between IPv4 and IPv6. I would be forwarding you them today in the class, in the Google Classroom. Here, some points that I would like to check. The first thing is expanded addressability. And what I mean by expanded addressability, you see the size here is 128. Now, if you see an address which looks something like 2001 colon 128 colon 76 colon 1, this denotes this is an IPv6 address. If you remember, we did networking commands. Within the networking commands, we did ipconfig or ifconfig. We got the list of IP configuration that we had within your system. And I mentioned there one of the addresses that this is an IPv6 address. And this is what we meant there. Nowadays, whatever systems you get, they are IPv6 capable. So this is the source and the destination address. There is certain fields like versioning is still there. We have a priority field. We have flow label. Payload length is there, next header, hop limit, and so on. That remains the same. I'll give you a comparison table. I think that would help us rather than going here one by one. You can then check what are the differences between the two packets, that is IP4 and IPv6. Now, presently we are using IPv4, all right? We need to move to IPv6. There are certain mechanisms by which transition can be done from IPv4 to IPv6. The first one is known as dual stack. This is tunneling. Let me first show dual stack, how it would look like. Dual stack means now we are discussing about transition moving from V4 to V6. The first one that I'll take here is dual stack. What do we mean by dual stack? Let's say we have a router here, okay, and within this router we have two protocol stacks. One is of IPv4 and another is of IPv6. So what happens? Say these are the links. If a packet comes which is of IPv, let me just say this is V4 and this is V6. If a packet comes here which is of, let's say, V4, V6, it would be taken care by the protocol stack which is V6 and then passed on to the link. And if a packet comes which is of, let's say, V4 here, this would be here by the protocol which is V4 because it has that stack. Let me just clear it. Oh. So if a packet comes here, now in the second case, we get a packet here which is a V4 packet. We would have a separate protocol stack which would take care of it and then pass it on to the link. This mechanism in which we have both the protocol available within the router, this is R here, this is known as dual stack mechanism. So to move from IPv4 to IPv6, one of the mechanisms is have both. You can have both packets moving across, whether it's V4 or V6. But it needs the routers which are existing within the network to be upgraded so that it has both. It may not be possible. So it may be difficult to have, both protocol stacks working on them. This is one of the method. The second method that you can have is you'll say that we'll completely move from IPv4 to V6, change all the devices, change all the routers, and have completely new devices. But then think about it, whether it's cost effective or not. You would need to have so many changes within the network, change whatever you want to have. That is, a difficult one. That may not be the way to do it. And the third one that we have is known as tunneling. We can't upgrade all the routers. We can't completely change all the routers. All right. So in fact, even having a mix of V4 and V6, some are upgraded, some are not. What to do in that case? In that case, we would use tunneling. And what is tunneling? Tunneling is basically keeping, now we have all the routers here which are V4 capable, which can pass on V4. Some are V6. So once a datagram comes from V6 to a router which is V4, let's say this is the scenario we have. On the left hand side we have A and B which is V6 capable. On the right hand side we have E and F V6 capable. In between we have two routers which is C and D which are V4. So what we do is we tunnel the traffic. We put on the packet like it's been given here. We hide packet V6 within a V4 packet. Okay. So then at this point of time, they would think that these would think that whatever we are transmitting in this case, we are transmitting V4 packets, and the data they have within the V4 packets is actually an IPv6 datagram. This is tunneling and it's a mechanism of transition from V4 to V6. See here, A to B is V6. C, okay, we put a V6 packet inside a V4 packet. Then C and D pass on simply like V4 packets. D and E, okay, again from V4 to V6 and then so on. Then E and F is V6, so we can have simple. So there are some given here, you know, figures in which estimates how many, people are presently using IPv6. There is a reason that IPv6 adoption hasn't been that much, right? I'll give you some work to discuss about it. We'll discuss about NAT and subnetting, which is presently helping you rather than going for IPv6. As well as I'll want you to have a look at SDN. The last part of the network layer is about ICMP. That is Internet Control Message Protocol. Let me see if it's somewhere here within the slides. I see. I don't see it here anyhow. It was taken in routing as well. If you have any doubts regarding the network, the routing lectures that I had sent on Google Classroom, please inform. We'll discuss that as well in the class. And otherwise, we'll move on to the transport here in the next section. Okay, so I have here the last part of it, that is the ICMP, Internet Control Message Protocol. Ramanand, what are you seeing this time? Right. All right. Thank you. Thank you. So ICMP is used by the hosts and routers as well as the gateways to communicate network layer information to each other. Basically, it does error reporting. So if you get a message that the host is unreachable or the network is unreachable, the port or protocol, this is the error message which is generated by ICMP. We saw the best example of ICMP as ping, which uses the echo request reply. That is given here. If you send a packet, ICMP basically has two fields. One is the type field, another is the code field. That's given here, type and code. So if this is the ICMP packet, you'll have two things. Now, if you have zero type, if you have code zero, this means you are sending a ping, right? You want an echo reply from the ping. If you get back a reply, that means it's a successful one. You are connected. It's a reachable host. And depending upon whether you had any lost packets and so on, how much time it took, what was the return trip time, and so on, you can get the details within this ICMP protocol. If it's not, it will give you an error that it's unreachable, you could not get to that. It comes under RFC 792. Example, the use of it is in telnet. Example would be FTP. Example would be HTTP. If you get an error message which says destination network is unreachable, think of it that its message origin is ICMP. This, in this case, it will be type 3 ICMP. This is often considered as part of IP, but if you see architecturally, it is above ICMP. Why? Because ICMP messages are carried inside IP packets. This is carried as an IP load. And the host receives this IP packet with ICMP specified as upper layer protocol, Remember just now we saw the packet format. There was one of the fields in IPv4 which had mentioned upper layer protocol. There I gave example of, that whether it is 6 or 16, whatever it was, it mentions it as UDP and TCP. Okay. But it's not necessary that ICMP can also be specified as an upper layer protocol. And the receiver would demultiplex it to understand that it's an ICMP message. There will be two fields within it. There will be type field and a field which I have mentioned, which I have marked here with the red ones. So ping can send these type, let's say 8 and 0 across echo request, which is given here as well. If it's 8 and 0 within the message, the destination host would see that it's an echo request and it would reply back with what? This 0 and 0. Let me just clear it. Explain it. Now I want to ping something. I would create an ICMP packet, that is this one first, in which I would send type as 8 and code as 0. The receiver receives it, demultiplexes, checks the upper layer protocol. It sees that it's an IP ICMP, type 8 and code 0. And it means that it's a ping request in which it should be replied back. And what is the reply that the destination would give? The reply would be this echo reply, in which we would have a type 0 and code 0 ping echo reply or ICMP echo reply. Another example we took that uses this ICMP is trace route, tracert command that you might remember that you have taken. This is basically what we have in error reporting. There are other, messages, types and codes which are given here. Destination host, reachable, unreachable, destination protocol, unreachable, destination port, unreachable. What is port? We'll take it in our next lecture. Route discovery 10 and 0. That is the trace route that we will use, or tracert command that we have used. So this is the example of trace route. We have done this in the lab, so it would be easier for you to stand here. And the next part is of network management, right? And we'll take it here. SNMP protocol, simple network management protocol. It's given here. The last point that we'll take here, ICMP is for IPv4. We use IGMP or neighbor discovery and protocols like that for V6, which stands for Internet Group Management Protocol, IGMP, if you're talking about IPv6. Well, I believe this should be the end of the network layer. In the next class, we will be taking up the transport layer. If you have any questions, all right, you can tell me, you can ask me now, or you can email me as well. I believe you have gone through the routing part also. It's an important aspect. You have to understand all the algorithms that are related to it, distance vector, Dijkstra, and so on. Also do a comparison between link state and distance vector routing. I'll also send that as notes within the Google Classroom. All right, Ramanand, I think I'll stop the lecture here. Any questions? All right, I'll see you in the next class then. Thank you, everybody. Bye-bye.